Now, we do need to be discerning when we use these rules. So one thing to be aware of is that saying a series is larger than some other series which converges doesn't really do a whole lot. And saying that a series is smaller than something that diverges also doesn't do a whole lot, right? The harmonic series is always larger than, say, the geometric series, 1/2, 1/4, 1/8, 1/16, and so on. But the harmonic series still diverges. That's not a useful comparison. Let's say I've got this series, 1 divided by quantity 2 to the power n less 1. Then I know that each of these fractions is greater than 1 over 2 to the power n. But again, knowing that this series is larger than something that converges doesn't help. So what other test, what other kind of comparison can I do? Well, we can also use what's called the limit comparison test. So if we have two different series, usually A sub n will be a series that we already know, and B sub n is going to be some other series that we don't know yet. What we're going to do is take a quotient of the terms of one of the series divided by the terms of the other series, and take the limit as n goes to infinity. So the nth term of my first series divided by the nth term of my second series. So as long as both the original series have positive terms, and this limit converges to a positive real number, then both the two starting series will either converge or they will both diverge. They have to have the same convergence properties. So this becomes a useful test to compare one series that we don't know to a series that we do know. So for this one in particular, let's look at this series, 1 divided by 2 to the n minus 1. And we are going to compare that to the series 1 over 2 to the n, which is a geometric series. And we already know the geometric series converges, right? My common ratio here is 1/2. So I'm going to set up this limit. Numerator is 1 divided by 2 to the power n minus 1, all divided by denominator 1 divided by 2 to the n. So I can rewrite that as numerator 2 to the n divided by 2 to the n minus 1. And that it'll be the same as 1 divided by 1 minus 1/2 to the power n. So as n goes to infinity, 1/2 goes to 0. So this limit exists, and it is positive. That means that both the series I started with have the same convergence properties. I know that this geometric series converges, so by that logic, 1 divided by the series summation of n equals 1 to infinity, where I'm adding up 1 divided by 2 to the n minus 1, that series must also converge.